in our previous lecture we were discussing about some issues about linear strain and volumetric strain, and we essentially mentioned at the end that we will relate the volumetric strain with a very basic principle, which is the conservation of mass. So, we will bring this in the perspective of conservation of mass, though technically speaking conservation of mass is not a topic of kinematics, but we will bring this in the perspective of the kinematics through the linkage with the volumetric strain. So, if you consider a control mass system, the control mass system, if it has a mass m, then you have the mass m is equal to density into volume. So, I am writing volume like this because we already preserved the symbol v for velocity. So, then we can write take log of both sides and take the total derivative of both sides. Now, by the definition of a system is something, a control mass system has invariant mass. So, this is 0. So, then it will be 0 is equal to 1 by rho. Now, what is the total derivative of density? The total derivative of density is and sorry 1 by v dv dt this is nothing but the rate of volumetric strain. So, in the previous lecture we already found out an expression for this. So, to simplify this equation, we have del rho del t, this is the first term, then we can combine u del rho del x with we multiply this with rho, so plus rho del u del x, so that becomes del del x of rho u. Similarly, we combine this with rho into dv dy, so this becomes and finally this is a differential equation for conservation of mass in terms of the Eulerian variables, and this is the famous continuity equation. So, in a vector form you can write this as we have to keep in mind that there are special situations for incompressible flow. So, for incompressible flow, if you look at this equation, for incompressible flow this is 0. In other words, for incompressible flow this must be 0. So, that means for incompressible flow the constraints are, the kinematic constraint is divergence of velocity equal to 0 and the corresponding reflection in the property is total derivative of density is 0. Does it mean that density is constant? May or may not be. This is something which may appear to be a new concept to you, but you have to understand this carefully. Incompressible flow does not necessarily mean that density is constant. Why? You look at this expression for incompressibility. So, incompressibility means essentially the total derivative of density is 0. So, that means sum total of this is 0. That does not mean rho is a constant, because rho could be a function of x, y, z time, but sum total of this will be 0. So, it could be possible that the density is changing, but the total derivative of density is 0. Such a situation is called as variable density incompressible flow. So, let me give you some example where this kind of situation may be important. So, let us say that there is a control volume in which there is a solid metal, it is getting molten, and let us say when it is melting through heat transfer its volume is expanding. When its volume is expanding, so this control volume cannot accommodate that extra material, so it will flow out, but neither the molten metal nor the solid metal are themselves compressible phases. So, this is a situation where density at a given point changes with time, but you know it is an incompressible flow. This is variable density incompressible flow. Okay. Now, so this is a very unique way of arriving at the conservation of mass, but there are other different ways of arriving at the conservation of mass, and I will try to relate whatever equation we have arrived at here with some other derivation which is maybe more familiar to you. So, the derivation is based on a control volume approach rather than the control mass approach that we have just adopted. So, alternative derivation control volume approach. So, let us say that there is a control volume like this, with x, y, z as the coordinate axis. let delta x delta y and delta z be the dimensions along x, y and z. Let m dot x be the mass flow rate along x and m dot x plus delta x be the mass flow rate at x plus delta x. So, now similar mass flow rate will be there along y and z. So, we are first considering what happens along x and similar balance condition we will write along y and z. So, what we can write is m dot in minus m dot out is the rate of change of mass within the control volume. Let us say in a physical way what it is, that mass is entering at a rate of say 10 kg per second and mass is leaving at the rate of 6 kg per second. So, the remaining 4 kg per second what it will do? It will increase the mass of the control volume. So, this is just a simple mass balance. So, m dot in minus m dot out means m dot x minus m dot x plus delta x, this is along x, plus similar thing along y which I have not drawn just for clarity, but it is there, and similar thing along z. Okay. So, now m dot x minus m dot x plus delta x, what it is? M dot x plus delta x is m dot x plus higher order terms in the Taylor series. So, what is m dot x minus m dot x plus delta x is minus partial derivative of m dot x into delta x. So, we can write the mass balance equation as minus this is along x, then this is along y, this is along z plus higher order term etc. Okay. Now, it is important that we write an expression for m dot x. What is the mass flow rate along x? M dot x is rho into this cross sectional area, that is delta y delta z into u. U is the velocity along this. Similarly, m dot y is rho v into delta x into delta z, and m dot z is rho w into delta x into delta y. To sum it up, you now have in the left hand side minus del x of rho u then plus higher order terms is equal to del T of what is mass within the control volume, rho into delta x, delta y, delta z. You divide by delta x, delta y, delta z and take the limit as delta x, delta y, delta z tending to 0. Why do you take the limit? Because you want to arrive at a differential equation. A differential equation is valid at a point. So, when it is valid at a point, you must shrink this volume to a point. So, if you shrink this volume to a point, then that is limit as delta x, delta y, delta z all tending to 0. So, you will be left with so you see that from this approach also we have got back the continuity equation in its differential form. Remember, this is a very important equation because this equation is a mathematical representation of the physical principle of conservation of mass in differential form. So, this has to be satisfied. Now, I come to a point which I want to clarify, that as a teacher, you know, whenever I in an interview ask a student that can you tell what is the continuity equation, immediately in 90% of the cases I have seen that the student jumps up and says A1 V1 equal to A2 V2, or in some cases rho 1 A1 V1 equal to rho 2 A2 V2, but nothing other than that. Of course, whatever the student has learnt as that equation in its own merit is correct, but first point is that is of course not the most general form of the continuity equation. Second is the student often misses a connection between that equation and this one. So, we will try to establish that. To do that, we will consider an example of a simple one dimensional flow with fluid entering here and fluid leaving here and rho is constant. So, the assumptions are one dimensional flow and rho is constant. So, if it is there one dimensional flow and steady flow. So, steady means this term is gone, one dimensional means these terms will not be there, and rho is constant means essentially it will boil down to rho will come out. So, it will be del u del x equal to 0. Let us take a second example where there is no guarantee that the flow is one dimensional, but there is only one guarantee that at the inlet and the exit the flow is one dimensional, that is here it is one dimensional, here it is one dimensional, in between you do not know what it is. So, in that case this will be replaced simply by the vector form instead of the one dimensional form. So, this is general incompressible flow. Now, you take a volume element within this, a volume dV, and you integrate with respect to this volume of the entire system, which in this case is like a nozzle. So, now you can use the divergence theorem. The divergence of V dV is nothing but V dot unit normal vector dA. This is divergence theorem over the area A that bounds the volume V. So, this is divergence theorem. So, if you do that, then what you essentially get out of here, this eta is what? Unit outward normal vector. So, unit vector in the outward normal direction. So, here there is a surface which bounds this volume, and there is a inflow and there is a outflow. Because these surfaces are not penetrable, fluid will not flow through this. Therefore, this V will be 0 for the lateral surface. Only at the inlet and the exit where the flow is one dimensional, you can write this U, rather unidirectional, because U is a component, U is the velocity which is there, which is a function of y. So, U, so at the inlet V is U. What is the unit normal vector here? This is the x direction. So, unit normal vector outward to that is minus I, negative of this, and the exit area again U there, but the unit vector now is plus I. So, that means minus integral U dA AI plus integral U dA over AE is equal to 0. By definition, integral U dA is U average into A. So, minus U average I into AI, and this is U average E into AE, this is 0. So, this leads us to the condition that AI UI is equal to AE UE. This is the so called A1 V1 equal to A2 V2. So, what are the conditions under which this is valid? The condition under which this is valid is that first of all, rho is a constant. So, effectively it gets cancelled from both sides. U is not local U, but it is the average velocity over the section I. This is the average velocity over the section E, and these are cross sectional areas of section I and E. average velocity and local velocity, they will be essentially same when the velocity profile is uniform, otherwise there will be a difference between average velocity and local velocity. So, to sum it up, we have discussed about various ways of looking into the continuity equation, the incompressibility constraint and different styles of interpreting and describing the conservation of mass. So, the next concept with which we will start very briefly in this session and we will take it further forward from here is the angular deformation. So, so far we have discussed about linear and volumetric deformation, but angular deformation is one of the great hallmarks of fluid flow. So, angular deformation means that if you have a two dimensional element in the plane of flow, this two dimensional element may arbitrarily deformed in this way. Now, we will not bother in the changes in length, but we will bother in the changes in angle. So, to what it means here is that now if we draw a horizontal line which is like along x and a vertical line which is along y. So, this angle delta alpha and this angle delta beta will be matters of concern to us. How do we find out the rates at which these angles change? We will take it up in the next lecture. Thank you very much.